Welcome again to the Deep Canyon Lecture Series. It's sponsored by UCR Palm Desert Campus, all of the partners who we've just recognized already, and the Department of or College of Natural and Agricultural Sciences at UC Riverside, and the UCR Natural Reserve System. Tonight's speaker is a fun one. Some of you may remember in the last series that we had a speaker who was lined up for March who got canceled at the last minute. That was Misty Peg-Tran from Cal State Fullerton. She was going to talk about whale sharks and piranhas. I called her up to ask her about this year's lecture series, and she said, "Yeah, sure, I'll do that. But I have this really rock star postdoc that you should get instead." And Misty said, "I'll come anytime." So she'll be on next year's list. So she dubbed in her postdoc, and who is interested in whales and microplastics and feeding in whales and other such things. And so I said, okay, that sounds like a great opportunity for us to kind of get two marine biology talks for the price of one. So Sherelle Kahana Rapport, did I get that right? Okay. It doesn't look the way it's spelled. So is tonight's speaker. She hails from the Great White North in Toronto. How many Canadians do we have in the audience today? Only one? Really? Wow. Okay. And she did her undergraduate degree in marine and freshwater biology at the University of Guelph. And then she went on to do a PhD in biology from Stanford on ecology and physiology of feeding in whales and the efficiencies and constraints that come with being a particular size, especially a large size that you might see in whales. And that included exposure to things like pollutants. And I think she's going to be talking about some of those things tonight. And now she's a postdoc at Cal State Fullerton, apparently the rock star postdoc at Cal State Fullerton. So, and tonight she is going to be talking about microplastic ingestion by baleen whales. How big a threat are the smallest smallest plastics to the largest animals? So please help me welcome Dr. Kahana Rapport.
Yeah, thank you. Okay, hopefully this is on. It sounds like it's on. Okay, it's on. Excellent. Thank you so much for that introduction. Dr. Peg-Tran is currently my advisor at CSU Fullerton, and at the end of this presentation, I will scoop her work a little bit. So next year, when she's here, you'll have a little bit of it in your brains already, I hope. These are just some fun videos from my time during my PhD, and we'll come back to all these great videos of whales. I started my undergraduate at the University of Guelph in Ontario, Canada, where I really started working with seabirds, actually, in Alaska. And we started using a tool called biologging, which is when you attach a suite of sensors to the back of an animal and let it go and live its wildlife. And it is mostly undisturbed, except for the moment where you caught it and put the tag on its back. And then it can collect data for you from the environment in a very natural way. So I really fell in love with that tool at the University of Guelph, which is how I moved over to Stanford University in Jeremy Goldbogen's lab. There's a marine station at the Hopkins Marine Station, it's called, in Monterey Bay. If any of you have ever been to Monterey Bay, you can go visit the marine station. And that's where I had the chance to do some of these cool opportunities, like see whales in the Antarctic and fly drones and work with these amazing creatures. So we'll talk a little bit more about that as well. But my work with whales has really transitioned to my work at Fullerton, where outside of nature, we can tag whales and we tag seabirds and work with them there, but we can also learn a lot in a laboratory. And so I integrated both laboratory work and field work to my questions at CSU Fullerton and really expanded my question a little bit more to a more integrative perspective. Please also let me know if you cannot hear me. I can speak up, move the mic closer to my face. Don't hesitate to interrupt me. without further ado, we'll talk about sort of this approach that I was alluding to. So it's a very multidisciplinary approach, which I think is really exciting. And we can integrate morphology, ecology, physiology, and conservation to answer really big picture questions. And I choose to answer these big picture questions on filter feeders. So filter feeding is a style of feeding that is found in all sizes of the animal kingdom, from krill to flamingos to manta rays to baleen whales. And filter feeding has evolved many times throughout history. You see it all the way back into before the age of dinosaurs, where most things lived in the sea. And when we look at the history of filter feeding and we look at filter feeding animals now, we see that one of the rules of life, one of these things that we see over and over throughout evolutionary history and on our Earth right now, is the world's largest animals are filter feeders. But why is that the case? And that is the defining question that has been my research program and will continue to be my research program. I am going to be faculty starting next year in Virginia. So please invite me back from the other coast. I'd love to come back, but this is that defining question. And so when we're talking about these mega filter feeders, we break them into three large categories for the large filter feeders. We can talk about the flattened filters. So that's something you see in a whale shark and in a manta ray. They are flat, they have lobes, and they're kind of smooth in appearance, but rough in texture. Then you have the stratified filters, which are found in a megamouth shark or in an oarfish, animals that most of us have probably never seen and likely will never see. They're very rare, but they're very large, and they are filter feeders that have hardened structures throughout their mouth, throughout their filter. And finally, we have the bristle filters, which you find in basking sharks and in rorqual whales or baleen whales, and these are the focus of my work right now. They're a bristle broom-like filter that sort of moves through the water, and we'll talk all about that. And so of these large filter feeding animals, my favorite group, of course, are the rorqual whales or the baleen whales, which are actually divided into two groups. You have the animals like the bowhead and the right whales. They're very slow moving. They sort of look like a vacuum going through the water. But then you have the rorqual whales or the lunge feeding whales. And they are the animals like the humpbacks and the blue whales. And they have a very dynamic feeding strategy, which we're going to see in this video. So this is a blue whale swimming up to a ball of krill. This is an illustration of what it actually looks like beneath the surface when a blue whale or a humpback whale feeds on krill. Maybe we can even watch it again just because it's cool. I love it. This is an illustration. So these whales are the lunge feeding whales, and there is quite a number of lunge feeding whales. There are 11 species of whales. They go from the smallest, the minke whale, which is about 7 meters, to the biggest, which is the blue whale, which is 23 meters long. So like the size of an airplane. And though minkies are only 7 meters, they are some of the largest animals on Earth. And the blue whale at 23 meters is the largest animal to have ever lived, bigger than all of the dinosaurs. So filter feeders are very large animals. The largest fish is also a whale shark. So there's something about filter feeding and large body size that we're going to come back to again and again. And to study these whales in nature, without interrupting their natural behavior, we use something called a customized animal tracking solution tag, or a CATS tag. And I'll keep saying CATS tag, CATS tag. And this allows us to record the animal's movements in nature without really disturbing them, without having to have a boat follow them around. And this is what it looks like when we put it on the back of a whale, a blue whale in Monterey Bay. Let's see if this will play. So that's my colleague Dave. You can vaguely see the blue whale underneath the surface of the water there. It'll come up to breathe. It's a mammal, so it's going to breathe. And we stick the tag on its back with suction cups, and the whale goes off. It does not care. And now this tag is on its back. And this customized animal tracking solutions tag, this CATS tag, has everything essentially that your iPhone and your Apple Watch have, but on the back of a whale. So it has a camera, it records sound, it has GPS, it has an accelerometer, so it knows how fast and where the whale went. And it has suction cups. So when it attaches to the whale's back, it does not hurt the animal. It's just like the suction cups you have in your bathroom tile, or like that keep something to your windscreen. And then eventually those suction cups loosen and they fall off, and the tag will float to the surface. And it has a little antenna, and we can hear that radio signal, and we go fetch it from the sea. And then we can download the data and see what that whale has done. And sometimes they stick for 2 seconds, but often they stick for 24 hours or more. So we get a real view into what that whale did that day. And so during my PhD, I had the privilege really to collect tags in many different locations in California, in Massachusetts, in the Antarctic, and in South Africa. And so I thought I would show you all a little bit what that looks like in each of these different places. So this is a blue whale. You may have seen this footage actually. This is from the BBC, but we were there tagging the whales at the same time. They just got really nice footage. This is a blue whale in the Southern California Bight, so really not very far away from us, feeding on a massive patch of krill. So that's a blue whale, which I think is amazing. You can really see how long that body is in that video. Then we have a humpback whale feeding in Stellwagen Bank off the coast of Massachusetts. Different species, a little bit smaller, about 14 meters. And these guys have learned to actually use the ocean floor to feed. They will put their face up against the dirt and use their flippers to scare fish into their mouth. So a different style of feeding than what that blue whale had been doing. And they do it in groups. Maybe you can see the flipper of its buddy. And then I worked in South Africa on the Broodies whale. So that's not a whale we would have seen in California. Another really good BBC clip of this Broodies whale feeding at the surface on fish. And some work we did there resulted in some conservation policy changes in South Africa. So I can talk about that at the end if we want. And finally in Antarctica, where I worked with minke whales, the smallest of the lunge feeding whales. These guys like to swim in groups of 4 or 5, as you can see. And that big bulge, that's their lunge feeding motion that we saw in that blue whale video, but on a smaller scale in a minke whale in Antarctica, where they feed on krill. So having the opportunity to do all of this field work and go to all of these cool places, all of it had a purpose in mind, which was to answer some questions relating to size and the different elements of whales' physiology, ecology, their morphology, and their conservation. So one of the first questions that I asked at the beginning of my PhD was about how whale body size affects their maneuverability, so their ability to turn and hunt and move in their environment, and their engulfment capacity, that thing that makes them really unique, that big ball of water that they can swallow, and how that relates to their size. And of course, I'm not the only person to have ever thought about looking at size. Even Galileo, he was the first one to actually write down a theory about body size way back. That thing was written in Latin and I had it translated. But basically what he was saying was that we can look at size through a perspective of scaling, the structure functional consequences of size change. So imagine when you make a house bigger, how that changes how the house is built. You can apply those same ideas to an animal's body. And so studying size allows us to see a range of things that occur in nature, like how the beaks of these birds change. And it also allows us to explain these things from a perspective of physics. So we're going to do a little bit of physics now. So this is something called the square cube law. This was in that first treatise that Galileo wrote. And the square cube law says that as things change size, they have a predictable relationship that will have a predictable result. So for example, when you increase the length of something, it will increase in length. Right? That makes a lot of sense. The length, when you add length, it increases in length and it scales in proportion to 1. So when you go from 1 centimeter to 10 centimeters, that scales in proportion to 1. But if you scale that same thing, if you increase its length, its surface area actually doubles. So when you increase the area of a sphere, for example, you actually double the surface area. So even though the diameter of the sphere is 10 centimeters, the surface area, the outside, is now 100 centimeters. And then when you have a cube, it triples, essentially, it cubes. So the volume of this thing that you only increased by 10 centimeters, its inside area has cubed, so it's 1,000. And so these are basic laws of growth that we apply to buildings, to bridges, to our bodies, and also to animals. So to put the square cube law into practice, we will talk about these fiddler crabs. So Fiddler crab have these big claws. Maybe if you've seen a fiddler crab before, you can recognize it. They have one small claw and one big claw. And this claw grows in proportion with their body size. So as the crab gets 1 millimeter bigger, the claw will also get bigger. Now, if the claw got bigger in proportion to the body size of the crab, so if the crab grew by 1 millimeter and its claw grew by 1 millimeter, you would call that proportional growth. That's predictable growth. And if you were to plot it, you get a line with a slope of 1. But in nature, we actually see that when the crab's body grows by 1 millimeter, its claw grows by a lot more than that. It has a disproportional growth. It actually breaks the laws of physics. This crab's claw does not do what physics intended or expected, but actually gets bigger than that. And we call that hyperallometric growth or positive allometric growth. And if it were to do the opposite, we would call that negative allometry or hypoallometry. So what's cool about this, what Galileo noticed and what we may notice too in nature, is that animals have the ability to break these laws of physics. These predictable rules with predictable results are not always seen in animals. And so how are we going to tie that to a whale? We're going to tie it to a whale to look at their flippers and flukes, which are the things that push it through the water. Those dictate its maneuverability and how it interacts with its environment. And we're going to look at its engulfment capacity, or how much water it swallows and how much food it can take in. And we're going to apply those predictable physics rules to these whales and see if they break the laws of physics. So one of the ways we're going to do that is by collecting data with drones. So we can fly drones over whales. It doesn't disturb them all that much. We can do it from a big height so they can barely even hear it. And we can take pictures of their flippers and flukes, just like we have in these squares, and measure the length of these flippers and these flukes relative to their body length. This 23-meter blue whale versus this 8-meter minke whale and this 11-meter humpback whale, for example. So we're going to compare their flippers and flukes and see how those flippers and flukes push them through the water. And the other thing we want to look at is their engulfment capacity. And so engulfment capacity is how big their mouth opens to swallow water. And that one is a little bit more difficult to get and is a more invasive measurement. And the way I collected these measurements was actually from historical whaling data. So way back between 1910 and 1970, there was a lot of harvesting of whales. And they harvested about 1.5 million whales just out of the Antarctic alone. And those whales were used for food and for their blubber was used for oil. But one of the things that did come out of it that you could call a benefit is that a scientist was allowed on board those ships that were harvesting the whales, and they took measurements of those animals. And sometimes they even kept the bones. So this is a blue whale that's in Vernon, actually, in a whale warehouse that we have that the Los Angeles County Museum has. So I could use measurements from this skull and from these historical whaling records to figure out the engulfment capacity. So from drones and from historical records, a very modern tool and a very old tool, we can understand if whales break the laws of physics. So we're going to do a little graph. So to infer maneuverability, so how the whale pushes itself through the water, we want to look at its fluke, which pushes it through the water, and the flippers, which also help move it through the water, but also change its orientation. These will tell us about maneuverability, so how fast the whale can turn and can hunt. And we can look at these control surfaces from the perspective of the square cube law. As the whale's body increases in length, we expect the flippers to grow in proportion. So not like this. This probably looks kind of funny, and you'd be right to think this looks funny. These are the proportions that we expect. And I wanted to know, are they the proportions I expect, or are they going to be disproportionately long? And so from drone footage and a little bit of historical data, we were able to see that they actually have disproportionately long flippers and flukes. So they broke those laws of physics. That predictable relationship is not found. The slope of these lines, what we expected, is not true. These whales can push themselves through the water with greater speed and ability than we had expected, than physics would have dictated. So that was pretty fun to discover. The other thing you need to consider when you're pushing something through the water is the mass of the object, because you can have a really big flipper and a really big fluke, but if you're kind of chunky, it's going to be hard to move yourself through the water. So we wanted to see how would the mass of the animal affect their maneuverability. And what we found was, in fact, these whales are very fat. They are bigger than physics would have dictated. So the mass of the whale is disproportionate to its length. So they are heavier and more rotund, you could say, than physics would dictate. So for maneuverability, that is actually a challenge. That means your very big body is being pushed through the water, but it is still harder to move your big body than your flippers can account for. So this is a bit of a physical challenge for whales. So we thought, what would you do if it's hard for you to move through the water? Would you maybe make your mouth bigger to make it easier to capture your food and a greater quantity of food at the same time? So we looked at their engulfment capacity. So these are all the things that make up the engulfment capacity. This engulfment capacity is what makes these whales so unique. It's what allows them to lunge. And it's composed of the ventral groove blubber. So that's the big neck pouch of these whales that expands, sort of like a pelican's does. If you've seen a pelican with a mouthful of water, this is that groove blubber, sorry. Then you have the bizygomatic width, which is basically just the width of the head. And then we also looked at the length of their jaw. And so what this allows us to do is look at this in a 2-quarter ellipsoid engulfment model. So a little bit more mathematical modeling for these whales. We just love putting physics back on these whales. And we basically treated this like a half a circle using all of these measurements. And we collected over 1,000 measurements from the historical record. So unfortunately, that is more than 1,000 harvested whales, but at least they helped us answer this scientific question, which is that these whales take disproportionately large gulps. So we expected them to have one size gulp, and they have a much, much bigger mouthful. So they have a much bigger mass and a much bigger mouthful than we expected. And so what does that mean for whales? It means that for a small minke whale, they're very agile. Their flippers help push them through the water with a lot of ease. They can go hunt in small crevices, which makes sense because they often hunt in the Antarctic where there are lots of ice flows. But a big blue whale has a much harder time moving its body through the water. But it has a very big engulfment capacity, which allows it to swallow a lot of water all at once. So even though they have a hard time chasing their prey, when they do catch it, they can eat metric tons of it all at once. About 80,000 liters of water is the total amount that a blue whale can swallow. That's like many multiple backyard swimming pools. So that's a fun one. So once we understood a little bit more about the morphology of their mouths on the outside, we actually looked inside their mouths. So baleen is the filter of these whales. It's that bristle type filter that I mentioned at the beginning that sort of acts like a broom, and it lines the roof of their mouth. On the bottom, they have that big ventral groove blubber, and at the top, they have a bristle-like structure called baleen. And for a long time, we thought that baleen acted like a sieve or a pasta colander. So if you think about when you have pasta ready, you have your pasta bits floating around in the water, and you take out your colander and you dump the pasta and the water into the colander. And the colander lets the water out, but all the pasta stays inside. And so that's kind of what we thought about baleen. That's how we thought baleen worked, except of course, instead of pasta, you have krill or fish. But we thought it worked like a pasta colander. And then there were some folks who studied balanids, so the whale that is sort of like a vacuum, the similar species, but not quite the same, that also has long baleen, but moves through the water like a vacuum, like a hoover, rather than lunging. And what they discovered was that the water actually flows past their baleen and out through a special hole on the side of their lip, and it goes past the tongue. So rather than working like a colander where the water and the krill went directly to the baleen, the water actually helped the krill flow past the baleen to the esophagus. This is called cross-flow filtration for anybody who's an engineer. This is often how we clean water in wastewater treatment facilities. This is called cross-flow, and humans have already come up with this, and maybe we copied it from whales, who knows? But this is a mechanism that we know about. And this works because they move their mouth slowly through the water. But as we keep saying, rorquals, they lunge. They do not move slowly through the water, and they don't have a special opening at the back of their mouth, at the back of their jaw, to let water flow out. So we did not understand how is it that rorqual whales are filtering their food. And this is significant because imagine if you have a mouthful of water and somehow the water has to get out of your mouth and the krill, your prey, needs to stay in. That gets caught, baleen, you're going to have food stuck in your mouth. You can't take your finger, right, and clean out your baleen. You don't have fingers, you're a whale. So we wanted to understand how it is that they have a non-clogging filter that doesn't work like their cousins, the balenids, and does not work like a pasta colander. So the first thing we did was take a good look at some living whales and take some pictures of baleen. Another thing that happens when you harvest a whale is you sometimes save the baleen. And so the museum in Vernon, the whale warehouse, also has a lot of baleen. So unfortunately, it does come from a deceased animal, but at least it does some good for some scientific inquiry. So this is what a piece of baleen looks like. It lines only the upper jaw of their mouth. This is that ventral groove blubber that makes up their engulfment capacity. And it's broken into minor plates and major plates. And this is what it looks like. And if you were to feel it, it feels like horsehair or even rougher, and it smells really bad. And blue whale baleen actually is dark blue in color. And all the different species have slightly different colors of baleen, from dark blue for the blue whale to a very light yellow. This is actually the natural color in the minke whale. And so we studied blue, fin, humpback gray, and minke whale baleen that was all in storage. And we wanted to look at the differences in these filters across the species to try to learn about how this filter works. Does it work like a pasta colander? Does it work in crossflow? Is it something else? So we took many measurements. How much space is there? How big are the holes in this filter? How long is the filter? How thick is the filter? How big are these bristly hairs that compose the filter? So, for example, we looked at the plate spacing between the species, and what we found was that blue whales have bigger gaps between the plates of baleen than the minke whales. The minke whales have very small gaps between their plates, and the blue whales have very big gaps between the plates. And this kind of goes along with the theme of the day, which is that the bigger whales have bigger engulfment and bigger mass. So this was not a very surprising thing that we found. But what was surprising was the hair of the baleen, the fringy part of the baleen, the broom-like aspect of the baleen that actually catches the krill. That is not different across the species. The slope of this line is not very steep. And what that means is that the hair diameter, the fringe diameter, the broom part of a blue whale's baleen is similar to that of a minke's. And that we did not expect. That was not like any of the other patterns we had seen in these whales. And so our next step was to look inside the baleen using CT scans and scanning electron micrographs, or SEM. So this is a non-destructive process. We can put this inside of a machine and scan from the base of the baleen all the way to the tip of the baleen. So the baleen starts out as a keratin sheath. So it's made of keratin, just like your fingernails, just like our hair. And it starts out as a sheath. And at some point, all the hairs break out and form that bristly broom-like mat. And what we found, or this undergraduate who I worked with, Meg, she found it, we found it together. We found that these tubes extend from the base of their gums all the way out. So it's a continuously growing feature. As they use it and as it breaks in their mouth, when it gets broken by water pressure or maybe even by krill hitting it, it is constantly growing. And these are the differences across the 5 different species. This is inside the plate of the baleen. This is a blue whale where you can see the tightly spaced pores. And this is a minke whale that has these really big pores, these big areas that hold the hairs. And this was a significant thing to us because we didn't even know how these bristles grew. Now we know that they grow in concentric rings. So when you're able to look inside something and look at it non-destructively, you can actually learn a lot. So we looked just now, we saw all of these hairs, but from the inside, the side or the tongue side of the baleen. This is what their tongue is rubbing up against all the time. And we wanted to try to figure out what is the space between all of these hairs. So when you look at a pasta colander, you can figure out how much water is going to flow out based on how big the holes are in the pasta colander. But this, I don't know about you, but I can't tell where the holes are in this thing, but I know that the water has to come out. So what we did was we actually looked at something that was very relevant to all of us just a little while ago. This is the inside of a KN95 mask. These are filters that have really, really small holes. You can't see them with your naked eye, but you know that there are holes in them because you can breathe through them. So we looked at the inside of a KN95 filter, and we said, if this filter can pass air through it, can we use the concept behind measuring the holes in a KN95 mask to apply that to a baleen whale mouth? And it turns out that we can. It's called the Kozany-Kármán equation, and engineers have been using it for a really long time to make porous materials of certain sizes. And so this equation, basically, if you look at this baleen, allowed us to calculate the space in between the hairs and subtract from that the space that the hairs occupy. We actually did this using a CT scan. So we put this whole big piece of baleen in a CT scanner, just like a person would use. It smelled really bad and people complained afterward, but it was for science, so it was okay. And so we put this piece of baleen in there and we were able to calculate this. And what we found, what was really exciting that we found, was that blue whales have smaller holes than humpback whales. And this was fun because for the first time ever, blue whales are smaller than the rest of the whales. Usually they have a bigger mass, they have a bigger engulfment capacity, but this time they had something small. They had really small holes in between the hairs of their baleen. And this makes sense because blue whales eat only very small krill. They can only eat one thing in all of the oceans. They can only eat krill because they are so big. It's hard for them to chase fast little fish. So they have to go after krill, which group in big balls, and they don't move very quickly. So blue whales can eat krill. And this, we know this from observing blue whales, but this also proved it to us as a result of their baleen. They have a physical limitation that only allows them to eat krill. And so why is this interesting? Why do I care so much about baleen? One, because I love whales. But the second reason is we can learn a lot about filtration systems from these animals. They have a non-clogging, continually renewing filtration system. If you think about your coffee maker, that cone of coffee, you have to throw it out every time because the filter clogs. But if you're a whale, you can't have a clogging filter or you can't eat. So we can probably learn a lot about non-clogging filtration systems from these animals and apply our knowledge from these guys into our daily lives. So that's why we care about baleen whales. And then the next thing we did was we looked at the ecology and physiology of these whales. So we began to ask questions. If we know a lot about the mouth, we know how much water it can swallow, we know how efficiently it can filter, how does that affect their ecology? And so this is a blue whale feeding off the coast of California. It's from that same BBC clip. Let's see if we can get it to go. Maybe. This is that full engulfment capacity. This whale just swallowed a bunch of krill. There's krill and water inside this big expanded ventral groove blubber. You can kind of see the water bubbling out of this whale's mouth. In there, there's krill and there's water. It's trying to just retain the krill and get rid of the water. It's about 80,000 liters of water. That's a ton of water, right? Like 5 backyard swimming pools, probably close to an Olympic swimming pool of water. And they do this over and over and over again. Not only is it going to be, so then we were wondering, is this a time-consuming process? Do they do this differently? Do blue whales do this differently than minke whales? Everything we know about the quantity of their engulfment and the work that their filter can do, how does that apply to their behavior in nature? And so this video gave us a quick insight into that concept right away. So on the left, you have a blue whale, and on the right will be a minke whale. And what I'd like you to see is the expansion of the ventral groove blubber. So let's get this video to play. And so this is the tag actually sliding down the blue whale's body because sometimes it doesn't stick so well. So you'll see in a moment, that is the expanded ventral groove blubber of a blue whale. And it just one big gulp, and it's working. It's working really hard to filter the krill out from the water. But in the same time that the blue whale has done this one big lunge, the minke whale is now on its third lunge. The minke whale is much faster at processing its water than a blue whale. And I wanted to know why this was. What is it about the engulfment capacity and the filter that allows this to be? And how does this affect their life out in the ocean? So We're back to some physics. We're back to some math. So earlier we said that the engulfment volume is a big mass of water. It's a volume of water, and we expect it to grow proportionally with the whale. So we expect that as the whale gets bigger, the volume of water will cube. And the baleen area, that bristly broom that we were talking about, it is an area. So we expect that to square in proportion to the increased growth of the whale. So as the whale gets bigger, we expect this relationship to be seen. We expect that the engulfment volume will cube and the baleen area will square in proportion to length. And what will that mean for the filter time? The water has to go through the filter, and the water has to be engulfed, and then go out through the filter. So that will affect the amount of time that it takes to leave the mouth. So we expected that filter time will increase in proportion to length. We thought that a minke whale will have X amount of time to filter, a humpback whale, and then a blue whale. And it will just increase in proportion to length, but in a predictable way based on their engulfment volume and their baleen area. And you can probably guess, because whales never do anything predictable, that is not what we found. We found that the blue whales have really, really big engulfment volumes, much bigger than we expected. And we found that was true for the minkies, for the humpbacks, for the fins, and for the blue whale. And what's really interesting is that the baleen area also did not behave the way we expected it to, but it actually did so in a negative way. So you might be able to see that having a bigger mouthful of water would be a positive, but the area through which you filter it is actually smaller than you expected. So it takes a lot longer, if you're a blue whale, to filter out your water than we expected. A lot longer, disproportionately so. A blue whale that goes to lunge, we predicted that it would take a blue whale that goes and has a lunge a long, long time to filter out its water. So what we did was we tested this with tag data, because all that previous data, that's based on morphology, that's based on drone records, that's based on historical measures, that's based on samples in a museum. But what about animals actually in nature? Because we have the tag data, we can figure that out. So these are the results of what comes off of those customized tags that we stick on the whale's back. We also get videos. So first we get how deep the whale went in the water. Then we know how fast the whale went through the water, and we know its orientation in the water. So if any of you have ever had a Fitbit or an Apple Watch, this is actually what that raw data looks like before it gives you a nice output of like, you ran 12 kilometers. This is what your phone is actually calculating. So first we calculated, where is the lunge? Where is that moment where the whale opens its mouth? And we could see that in the video. So not only could we see it in the tag data, we could also prove it to ourselves using video. Then we could see the mouth closing. We know that this happens at the sharpest deceleration in speed. So their mouth opens really, really wide, and they have this forward momentum that's sending them forward. And when their mouth is full of water, sort of like a parachute, they stop short. If you've ever seen a parachute, the person using the parachute is falling quite quickly until they open the parachute and it stops them. That is essentially what happens to a whale when it opens its mouth. And then in this period of time, they're filtering. We could see that in the videos and also in the tag data. And finally, just before the end, we can see the ventral groove blubber has completely flattened out. And then they start fluking again, getting ready to do their next lunge, to go eat some more. And so we wanted to know, how much time is this filter time? And we wanted to compare it across body size again. All these questions go back to body size. So we tagged and droned blue whales, fin whales, humpback whales, and minke whales, all feeding on krill, either in California or in Antarctica. And these are the tags. So just to give you a relative sense of how the tags are, these tags, this one on this minke and this one on the blue whale, it's the same tag. It's just a much, much bigger animal. It's 23 meters versus 8. So the perspective of the tag really changes. So what we predicted was that filter time would increase in proportion to length, but not as much as we thought it would. And in fact, that is what we found. We found that larger whales filter a lot slower than we thought, because they have a big, big mouthful to filter out of not so big holes in their mouth, right? If we think about that morphology study we did, we found that the blue whales have the tiniest, tiniest holes, and that affects the area and therefore affects the speed at which the water can flow out of their mouth. So they have this increased filter time. So this led us to ask other questions. If they have this increased filter time, which means it takes them a long time to take one bite and then the next bite, how does that affect how long they dive for? How does that affect how many lunges they do in a dive? And how does that affect how much water they can process overall? And so we first looked at their dive duration. And what we found was that bigger whales do bigger dives. They stay underneath the water for longer. They have an increased dive time. Then we looked at the typical lunge profile. So we looked at hundreds of whale tags between these blue whales, these minke whales, these humpback whales, and we looked for a typical lunge. A blue whale typically does 4 lunges in a dive. So they dive down to where there's a patch of krill and they take about 4 big mouthfuls from that patch of krill. Whereas a minke whale will dive down to a patch of krill and take about 8 bites of that patch of krill. So they take about double the amount of lunges that a blue whale does. So you have an increased lunge time. Finally, we looked at how much water they engulf per dive. And we know that those blue whales have these really, really big mouthfuls of water. And so in those dives, blue whales engulf more water on those dives. So what that means is that even though a blue whale goes down and opens its mouth only 4 times underwater, and the minke whale goes down and opens its mouth 8 times underwater, the blue whale still swallows more krill and more water when it dives down. Now, you might be wondering, how does this affect their ecology? What's the big picture here? And so if they have increased filter time and increased dive time, so they're spending more time underneath the water, what that means is they actually have a decreased lunge count. The blue whales are so busy taking so much time filtering out the water from their mouth that they actually have less opportunities to feed. They have less foraging opportunities. And they also have more water to go through. And so what that means in the long term is that they're more susceptible to changes in their distribution. If they only have 4 opportunities to feed, whereas the minke whale has 8 opportunities to feed, if you disturb a blue whale while it's eating, it's going to be harder for them to recoup that loss. So blue whales are therefore more susceptible to changes in their prey distribution and to human activities. And we see that when we study them relative to boats as well. When we study boat noise in whales, we see that blue whales are a lot more sensitive than minke whales and even than humpback whales. Now, how does all of this tie into their conservation? How does it tie into something that we humans can do to help these whales continue to thrive and survive on our Earth? And one of those big questions that's affecting a lot of animals these days is microplastics. Microplastics are everywhere, and they have been increasing 20-fold in the last 50 years in our oceans. And human pollution and microplastics can affect our marine ecosystem in basically 3 big ways. So the first is that microplastics can be a vector for pollution. So they aggregate other dirty things to them. Other animals can actually eat microplastics, which makes them think that they are less hungry because they eat a material that fills their belly but isn't actually nutritious for them. So it affects their growth. And when animals do eat microplastics, those microplastics can break down even further and release things like endocrine disruptors, which affect their growth and reproduction and even their mortality. So microplastics are a big problem that's been increasing in our oceans. And it also uniquely affects filter feeders because filter feeders, right, they swallow big masses of water. And if there's microplastics floating around in those masses of water, those microplastics can actually get ingested. And so this paper was done by Germanov et al., some people who work in Australia, and they went and looked, where are there microplastics? So that's from blue to red. So the more red you see, the more microplastic there is in the water. And where are whales? That's those hatch marks. So you can see there is an overlap between where the whales are and where the microplastics are in the ocean. And so we looked at this, and this got us very concerned. But there were 2 things about this map that we thought were missing. One is that this only looks at whales at the surface. This only looks at the microplastic in the top 1 foot of water. And we know that whales feed at depth on krill and on other items at depth. And a lot of this microplastic, these areas in particular, this is only where whales reproduce, and they don't eat while they reproduce. They tend to reproduce in warmer waters. So we wanted to know if in a place where we know that whales forage at depth, like off the coast of California, in colder waters up here, are they encountering microplastics? So we used those custom animalized tracking solution tags, those CATS tags. We tagged whales in the California current all the way from San Diego to San Francisco, and we collected water samples as well that collected water and microplastic from various depths, all the way down. Yes, that's okay. Oh, sure. It's any piece of plastic that is smaller than 1 millimeter and bigger than 5 nanometers. So it's like the back of an eraser on a pencil. Yeah, it's like this big. It's like your pinky nail and then smaller. You wouldn't be able to see the smallest microplastic size with your eye. So very, very small and difficult to collect. Yeah. That's an excellent question, because we're actually working on figuring that out right now. Someone in the PegTran lab has gone out and collected plastic and is trying to figuring out where it comes from. A lot of it comes from tires, actually. Tires, when they wear down, it gets on the road and the rain washes that into the sea and into the drains. So a lot of plastic comes from tires. A lot of it comes from clothing as well. Any clothing that's made of like anything poly that you find in the sea as well, and also fishing line, of course. Anything that comes from fisheries ends up in the sea. Yeah. So microplastics are really, really small. You can see some of them with your eye, but most of them you can't. But animals can consume them, and on purpose or by accident. So these whales are in areas where there are high levels of microplastics. And so we went and sampled all these different depths from the surface all the way down, even past where whales forage, past 1,000 meters. And these are the places where we did that. From San Francisco Bay to San Diego, the triangles are where we collected microplastics, and the circles are where we tagged whales. So we tried to get a really good overlap of plastic at the surface, which is a hollow triangle, to plastic at depth, which is a filled-in triangle, and whale tags all along. So that's me and one of the other students who I worked with, Lauren, collecting those data. And so what we wanted to figure out was a twofold question, because whales can ingest plastic, in our opinion, in two ways. They can collect it directly, so from the water. When they do that big lunge, if those microplastics are out there floating in the water, they can engulf them by accident. Or, I don't know why that was moving on its own, sorry. Or they can collect it indirectly from inside of their prey, because there's a lot of data that shows that krill and fish actually consume microplastic. And if the whale goes out and eats those animals, then they will be ingesting microplastic indirectly. So direct and indirect. And you'll keep seeing direct in blue and indirect in red. And so what we did was we tagged these whales, some blue whales, humpback whales, and fin whales off of the coast of California, and we plotted where in the water column they feed. So this is where a krill feeding whale off the coast of California feeds, around 200 meters in depth. So not at the surface, not where that map showed, but at depth. And then there's also the fish feeders. They feed closer to the surface. And then this is where all that microplastic in the water column data that we collected is from. And you can see there is a peak around 200 meters in depth, which is exactly where the whales feed most often. And so when we put this together, we were so concerned, because now we know that they take these really big gulps of water. They have filters that are very efficient at collecting prey. We know that they eat a lot of prey over and over throughout the day. And so we combined all of that into a scenario. So what we did was we plotted a few scenarios, a low, medium, and high scenario, to calculate the risk overall. And the reason why we needed to do scenarios is thus. Not all fish that they eat always have microplastic in them. About 1 in 3 of the fish that these whales commonly eat has microplastic in them. And about 1 in 20 krill may have a piece of microplastic in them. And this largely depends on where you collected this fish or this krill. So off the coast of California, this is often what we see. 1 in 3 fish has a piece of microplastic, and 1 in 20 krill has a piece of microplastic. And based on the morphology study of the whale baleen, we were able to assess that they could probably capture 50% of the microplastic that they encounter loose in the wild, not within their prey item, but in the water, just floating there. And so what that means for these whales is the red box plots here, where'd my mouse go, are the direct, and the blue are the indirect, and the blue are the direct. So what do they consume through their prey versus what do they consume through the water? And what we found was they consume a lot more from their prey. That is the bigger place where they get risk. That is the greater risk to them when they are foraging, not just it floating in the water, but actually being in their food. And so this basically means that a blue whale could eat about 10 million pieces of plastic per day. That's what that number is there. That's about 10 million pieces of plastic per day for a blue whale feeding off the coast of California, about 6 million pieces of plastic per day for a fin whale. Oh, I don't know why is this is rolling on its own. About 4 million pieces of plastic per day for a humpback whale that's eating krill, and about 200,000 pieces per day for a humpback whale eating fish. So those are some pretty scary numbers. That's a per day calculation. And so what that means is, as that question was previously asked, which was a perfect question, how big is microplastic? Not only is the size range pretty large, but how much each piece weighs is not always known. There's a pretty big range. From 0.2 to 4 milligrams is about the range of a piece of microplastic. And when we calculate that, when we say about plastic in 10 million pieces per day, that comes out to about 44 kilograms of microplastic per day. So imagine if you were going out and you were eating and you were getting 44 kilograms of useless garbage food that also could really negatively affect your organs and your endocrine system. So that's what whales might be encountering, and that's just the medium risk scenario. This is an environment where there's some amount of pollution mitigation. But when we look at a high scenario, you can predict that 1 in 7 fish will have a piece of microplastic in them. This is died. Oh, there we go. 1 in 2 krill will have a piece of microplastic in them, and their baleen will actually capture about 75% of the microplastic that's in the water, just because there's more microplastic in the water. And so what that would mean is that a blue whale eating will actually consume about 672 kilograms of microplastic per day. And that's in environments that are closed seas, like the Mediterranean or in the Yellow Sea in China. So these are some pretty scary numbers that we calculated for places where we know whales live that are near human population centers. We also wanted to see what would be true for a place like Antarctica, where there's a lot less humans, a lot less human pollution, but the whales still tend to go there to feed. And so in Antarctica, about 1 in 50 fish will have plastic in them, 1 in 70 krill. And because there's less plastic in the water, the baleen will capture only about 25% of what it encounters. So it's already, you can tell it's a much lower rate. And in a low scenario, in a place like the Antarctic, they will only eat about 1 kilogram, 1.5 kilograms of microplastic per day. So what's good about this, what's relieving about this, is that there is less microplastic in these environments where they do forage, but we do have an increasing problem, which is that they're increasingly encountering microplastic through their prey. And so we can mitigate this to some degree by improving how much of our waste goes into the seas. We can be more careful about how our storm drains let out water. We can be more careful about recycling and recycling properly, and how we dispose of our trash. So that's a little bit doom and gloom, but it's not too terrible, I hope. And I'm happy to answer any more questions about this in particular. Yes. Yeah, that's a super good question. That's something that we are working on right now as well. We do that by collecting their poop, which is not a super easy thing to do, because you have to be right behind them to capture it. And we don't know. But what we do know from taking blubber samples from them is that they absolutely do have breakdown derivatives of microplastic in their fat. So it's staying in their body and it's being broken down in such a way that it's being absorbed into their fat. And that's a risk because they use that fat to grow, but females also use that fat to feed their young. And so they're passing on things like PBDEs, which maybe you've heard of, or BPA to their young. It's not super high because it's not actually microplastic. It's not actually pieces of plastic. It's the chemicals that break out of the plastic, that compose the plastic. It's not like 100% of the fat, but it is still there and we're working on it. Unfortunately, it's a very slow process to learn those numbers, but hopefully I'll be back with those numbers. Yeah. 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 Yes. Yes, and so they're being done in mice and fish. Yes, it is being done slowly in mice and in fish. It's useful, but at the scale that is a whale, it's really hard. So the question was, can we do these experiments in other animals to figure out and then scale up basically for whales? And the answer is yes, but it's very difficult to scale to an animal this large. But what they're finding in fish is that it increases their mortality, like they lose a couple years of life if they're eating too much microplastic, and their reproduction is really bad. So their eggs are lower quality, and so therefore their young are of lower quality. So it's affecting the long-term population. Yeah. I can answer more questions. I can also talk about manta rays. So we can do a couple more questions, and then we can talk about manta rays.
You know what would be great if you did finish, and then
Sure.
we go to the questions.
Okay.
That way Nancy and I can pass out microphones, because
Excellent.
with the
Sorry.
recording, we can't hear any of the questions unless you're talking into
okay,
a
I'm
microphone.
sorry. Okay.
It's not, no, no apology.
We'll just, we can, I realize that we've almost been an hour, so I'll just mention that manta rays are another species that we are studying for risks of microplastics. So this is a very similar map as to the one before. Whoops. And it's also in darker red, you can see where there's increasing levels of surface microplastic, and the lines are where there are manta rays. And so this is also a great map, but a not quite perfect map, because manta rays, just like whales, don't only feed at the surface, and this doesn't cover all of the places where manta rays feed. So during my postdoc, I was working with Dr. Peg Tran at California State University, Fullerton, to improve on this map and calculate how much microplastics manta rays will ingest as well. And I won't go into all those slides because it'll take quite a bit of time, but manta rays have this very unique filtration mechanism, one that humans did not think about. So it is not a sieve, and it is not cross-flow, and it's not what whales use either. It's called ricochet separation, and basically, this is the manta ray feeding, which is just fun to see. They go through swarms of krill, just like whales do, with an open mouth. So it's really similar kind of in concept, but they have a flattened filter that does a different form of filtration. This is the inside of a manta's mouth. And I'll just skip past these, even though they're really cool. I feel like we are going on a little bit long, but they have these flattened filters that have holes in between them that we actually can calculate. Unlike the bristle broom-like filter of a whale, these actually can be calculated. And what we've done is actually put these into a tank, and we can see that a particle, rather than going down where those blue arrows go, it ricochets, it bounces off the surface of the filter, and it flows into the back of the mouth while the water goes down those pores. So it kind of does a hopscotch into the back of the mouth. And that's not something humans have ever figured out how to do. We've copied a lot of things from nature. So like our trains look like the noses of birds. It's called bio-inspiration. When we look to nature for solutions. And so what we're trying to do is convince people that the manta ray filter would be very effective for cleaning up our wastewater, because it's really good at capturing particles and it doesn't clog. So that's our next line of work. And oops, I think we will stop it there, because it's been quite a while that I've been talking. So I'd love to take any questions.
Okay, and raise your hand. Okay, I'll come to you, and then talk into the microphone. Hopefully this is working. Does it sound like it's working? Okay.
Is it working?
Yeah,
Okay.
I think so.
Recently, I was in Magdalena Bay looking at the gray whales, and they said that that population a few years back had lost hundreds of whales, and I was just wondering if you know if that has any connection to the microplastics.
It may. Do you remember what kind of species of whale it was?
It was great, the gray whales.
The gray whales?
Yeah.
So gray whales are very interesting because they like to eat in shallow waters, and they forage actually by putting their face against the dirt, and they make big holes in the sand, and they suck up both dirt and prey. And then they somehow filter that out, which is like a mystery to me still. But they clear out their filters and they retain their prey, but they are also definitely retaining microplastics in there because microplastic likes to settle in the sediment. And so that's a line of work that's being done at Oregon State University. They're collecting dirt from where they see gray whales feeding, and they're testing that dirt for microplastics. And it's possible, but gray whales have been stranding for they strand in big numbers. And they also think that's because they're very social and they like to do things in groups. And because they do those things in groups and they forage in shallow places, there's even some idea that it might just be the tides, that they just get caught by the tides, which would be a shame. But we don't know yet enough about microplastics to be sure if it's somehow like affecting their brains. It's probably just an unfortunate group behavior. Yeah.
Are you changing are you giving any of this information to the various governments where they're changing their
Yes.
policies towards disposal of plastics and other poison really that they're putting into the oceans?
Yeah, we're trying to. So the microplastic work that I was talking about, I know that it was up in Sacramento. I know that it was red. Someone called me and asked me to make a white paper about it, essentially, like a policy brief about this work that we had done. So I know that it reached somebody in Sacramento. I hope so. The way that we're working on it now is by actually going to private industry and going to companies like Patagonia, who actually has a grant for this kind of thing. They're interested in improving how you wash your clothing, because a lot of clothing releases lots of fibers and particles into our water. And so they're looking to improve either how we wash our clothes, maybe we wash it in a bag that we can retain plastics in, or even put a filter on the back of our laundry machines. And so before the water goes out and down the pipe, it actually gets diverted over a filter. And so those plastic pieces can collect and the water can go out. It seems, unfortunately, that the way might be through industry, but I encourage everyone to call their local politician and ask for improved wastewater treatment, because that might be the way too. Yeah.
I don't know if you want to put it with on a microphone. Oh, there you go. Has anybody looked at the increase or decrease of microplastics over time in the oceans?
Yes, they have. So there was a graph that I tossed up there, but basically we've seen a 20-fold increase in microplastic in the water over the last 50 years. People are constantly sampling water and looking for microplastics now. It's become a very big thing. I just read a paper about the rivers in China, a whole series of rivers in China where they're constantly monitoring. It's actually a government policy to monitor the microplastic levels in their rivers and in their basins. I wish the United States would do it too. I'll repeat the question.
Is there any way to tell if the percentage of microplastics is changing over that 50-year period?
That's the hard part, because we haven't been collecting the data for long enough, unfortunately. I don't think we realized the risk at the start. Like many things that we do, we don't always think about the long-term effects. And so for some places, we have a really good baseline, but not for enough places. And so we can see the overall increasing trend, but there isn't data from 30 years ago that I know of about the water in California from microplastics specifically. We've been monitoring fisheries, we've been monitoring fish, we've been monitoring water temperature and water salinity, but we haven't always been collecting samples to test. But I will say that some of the microplastic data we used was from 2016. So we have at least data from 2016, and we can see that it's been steadily increasing, especially in Monterey Bay. Yeah.
There must be different kinds of plastics.
Yes.
that release different kinds of basic chemicals.
Yes.
Molecular derivatives. Some of them, like this. Some of which, some plastic of which result in more toxic waste
Yeah.
breakdown of
Yeah.
products.
Yes, definitely. They're not all plastics are created equal, of course. Some of them break down differently. So we know that some plastic bottles, for example, have BPA, others do not. We could probably formulate plastic differently. I actually don't know enough about how we make plastic to say, but yes, there are differences. Some of them have more endocrine disruptors than others, for sure. It would affect the organism at the end point, what it's made of.
Sure, and if you found that one type of plastic resulted in more chemical waste products,
Yeah.
then we could concentrate on that.
Yes.
That would be a huge
That's very true.
for going forward.
Yeah. No, yeah.
I have a basic question of, we've been talking about the filter
Yes.
and the water that it was contained in.
Yeah.
So I guess I probably missed the understanding. The water comes into the mouth.
Yeah.
The mouth closes. Sorry, the mouth closes.
Yeah.
Then it's actually you have to, the filter itself, the water that has to be let loose by the whale
Yeah.
has to go through that filter and
Yes.
then have a means of getting out. You mentioned that there was a couple of the species
Yeah.
had sort of like a gill type.
They have like an opening at the back of their jaw, basically, that just like the jaw kind of disconnects. And
It's
yeah.
like a gill opening, though.
It doesn't go through a filter like a gill is, but yeah, it's
Sure.
like yeah.
Right,
Yeah.
but there's an opening back there.
Mhm.
The others don't have the gill.
No.
So they got it in their mouth.
Yep.
What do? Spit it through the filter?
This is why I have a job, because we don't know.
Wait, let me get this straight.
We don't know.
You don't know how
No.
the water has to be expelled.
The water is expelled and the krill is retained, but it's on that broom-like, it's like on these very, very fine hairs. And somehow,
On the inside of
yes,
the
it's
filter.
the krill is on the inside of the filter and the water goes out and through. I wish I could show that.
The filter. So there must be, you can see the animals opening their mouth and
Mhm.
stuff coming out after they have a big gulp.
So they'll take this really big gulp, right? And the water and the krill will rush into their mouth. And it's all swirling in a mass. And then eventually the ventral groove blubber slowly contracts and pushes that krill up against the baleen filter, which traps it inside, and the water goes out. They just open their lips like a tiny little bit.
So a picture you showed us.
Yes.
It's open a little bit.
Yep. And then, so based on the tag data and the morphology data and the anatomy data that we did, we know that somehow that water has to go out and that it takes them like 90 seconds and the krill stays in. But we have no idea how the krill gets off the inside of the baleen. None. Absolutely none. It isn't a cross-flow filter. It's not a colander. They do have a big tongue. And people always ask me about that. Their tongue has no muscle. It is a completely useless sack of nothing. It's really, really weird. It is not a muscular tongue at all. And so I also thought this. I thought maybe they could lick off the inside of the baleen. Nope, they cannot. We do not understand it at all. And it's literally why I have a job, because everybody wants to know, how does the animal with the world's largest filter, this filter that's extremely efficient, they have no way of cleaning it with their hands. They do not clean it with their tongue. How does this work?
Lauren's here to turn on.
Yeah, I was thinking maybe if we could have the video come back, if we can. I mean, and just put the PowerPoint, if we can just put the PowerPoint back up and then I can show them. It's a very frustrating question. I know. Yes.
You said that
No, it doesn't have muscle.
that on the maximum amount of microplastics that they would take in 672 kilograms.
That's the max, yeah.
That translates to about 1,482 pounds. How much food do they need to survive? I mean, 1,500 pounds, that's a lot of
They need a lot more food than that to survive, luckily, definitely. They eat all day long, like they will do like 360 lunches a day, and they will eat 270 days of the year. So when you look at it from a daily perspective, it's not a lot, but if that stuff is staying in their gut, if it's somehow absorbing into their body, that's when it becomes a problem. That's when it's a cumulative problem. So because they are where they are on the food chain, they eat this tiny little animal, but they eat so much of it, and that's why we think it accumulates. But relative to the scope of how much krill they eat per day, it's not that much. It's a very small fraction. It's just the concern of the accumulation over time. Does that answer your question? Yeah. Their metabolic rate is kind of weird. We've been trying to predict, do you know about the law of metabolic rate? There's like, right? So they fall on a weird scale of the metabolic rate. They're trying to determine, my colleagues really are trying to figure it out. They're trying to use drones to see how much oxygen they expire. You can do that with a drone now, which is really cool. But nobody knows exactly what their metabolic rate is. But I'm not sure if it would affect how the microplastic would break down, because they have four chambered stomachs that can break down all the chitin of their krill, so they're quite strong. Yeah. Yes, exactly. It could affect the amount of food that they have to go after if they perceive themselves to be full and they're not, or they go after not enough. Yeah.
I have a question.
Yeah.
I noticed on the map two things. The Mediterranean was completely red,
Yes. Sorry, we'll go to
and the Sea of Cortez didn't have
this map.
anything at all. It was white.
Yes.
Now,
Yeah, this map is from 2018.
okay.
So I don't know how up to date it is. I have not gone to the Sea of Cortez, unfortunately, to collect microplastic. I would love to, though.
Yeah, it's the aquarium of the world,
Yeah,
Jacques Cousteau said.
it is. It is an amazing ecosystem, and it is a closed system, at least on two, or even you could even consider it closed on three sides. I think part of the reason why there's a little bit less concern for whales, at least, is that down there, they're often not eating, just reproducing
Right,
and just rearing their
reproducing.
calves.
Yep.
So they aren't opening their mouths down there, really.
Okay.
But if their prey is picking up plastic in the Sea of Cortez and bringing it north to the places where they do forage, then that would be a problem. So it would be very worthwhile to go down, collect water and prey in the Sea of Cortez. Yeah.
Now, the red in the Mediterranean,
Yes.
why is that? Why is it totally red?
The red here it's an increase in surface microplastic water, like microplastic in surface waters. Sorry, that's why it's so red. And it makes sense because humans have lived along the Mediterranean for such a long time and have been dumping and polluting in the Mediterranean. We tend to treat the ocean like it's like an infinite place where things can dilute. And this map should go to show us that it is not. You know, you get the giant Pacific garbage patch. That stuff does not disappear. It does eventually accumulate, and it accumulates in population centers where people eat the fish that are in the Mediterranean. Those fish are definitely eating microplastics. 1 in 2 fish out there have microplastics in it. It's like not a good situation. It's not all bad, but it's not great. Any more questions? Yes.
Yeah, I think you said you could tell us about some change in South Africa because
Yes.
of your work.
Yes, so that's right. Thank you for reminding me. So we tagged Broodies whales in South Africa. So they're a mid-sized, lunge-feeding. They're a rorqual whale. They're not super big, but they're really fast. And in South Africa, they feed on fish. And their way of feeding on fish, because they're so fast, they're very agile. They have that excellent body morphology. They're not very fat, and they have really long flippers. So they're very agile, and they can chase balls of fish, and they chase them in circles. And in South Africa, especially in Plettenberg Bay where we worked, there is a octopus fishery. And the way you catch octopus is you have a float, and then you leave a line that goes down, and then you put a pot, and then it has a loop, and then there's a pot, and then a loop, and there's a pot. And if you're a whale and you're chasing fish around and around and around, you get entangled in those lines. And so what was happening in South Africa for a couple of years is that the whales were washing up deceased, entangled in octopus fishing lines. And they didn't understand why that was happening. But when we went and we tagged those whales, we could see their behavior. We could calculate how quickly they were moving and where they were moving and the types of behaviors that they were using. And we could see that they were going in circles. And we could see that they were doing that directly where there was octopus pots. And so they actually presented, my colleagues who did this work with me, they actually presented this data, and they have changed when the octopus fishing season is. And they're trying to have better release on the pots, which is something that we're also trying to do on the East Coast, to have better lobster pot releases. So whales get entangled in those pots a lot as well. Trying to improve the line, they're trying to improve the release, but they've also changed the rules of the fishery. And so we have a rule here in California where if a whale is entangled in a crab pot, if there are 3 deceased whales that are entangled in crab pots, the fishery closes. And people really don't like that, which makes sense because it's their livelihood, but they're trying to pass that rule for octopus in South Africa. And it's because of the tag data. So that's pretty cool. Yeah. Thanks.
That's a neat positive. I don't think, is this on? Yeah. That's a neat positive way to wrap this up. And I think we'll go ahead and bring this one to a close.